Hey, it's Joel. I'm in spring break, capital of the world, Grand Ledge, Michigan at 3D Ceram Sinto. And the reason I'm here is to talk about ceramics. Not just the porcelain that your grandmother has behind a glass case that you're not allowed to touch. We're talking about alumina and zirconia-based ceramics, technical ceramics, 3D printable ceramics, the kind of ceramics that can go inside your body to help your bones heal, or the kind of ceramics that can act as a heat shield for a spacecraft entering an atmosphere. And that's important because this poor mini Joel needs some protection. So let's go inside and talk 3D printing ceramics. I'm here with my friend David at 3D Ceram Sinto. Hey, man.
Hey, how are you, Joel?
I'm good. Well, I'm good. My little mini Joel, he's been better. So ceramics, I hear, while, like I said, not for my grandma's porcelain in a glass case, there's a technical ceramic category, and it could help us keep mini Joel safe.
Yes. So while we're talking about heat shields or protective ceramics, they are not thermally conductive, those types of ceramics. So you can use it as a protective device while you're re-entering the atmosphere, while you're traveling at extreme speeds, or while you're trying to protect something that's sensitive and needs thermal protection. So that's one of the many applications for ceramics.
Well, and these types of ceramics are 3D printable.
Yes.
So I have a machine right here next to us. Yes. It's capable of printing these ceramics. Can we go over the process of how this actually does it?
Absolutely. So what we'll talk about here is the 3D Ceram C101, and this is our laboratory version. So what this does is dispenses a ceramic in a resin, a photopolymer, and then recoats it. This will actually move forward, put a thin coat down, and then the laser up here will fire and cure a shape. And then this small platform descends and descends and descends, layer after layer, similar to your traditional original SLA printing.
Original, right. Because now when we talk about lots of MSLA and DLP resin-based 3D printers, there's a 405 nanometer light and it emerges from the goo.
Right.
And so this descends into the goo.
Correct.
What's the reason for doing it that way?
So ceramics are very heavy for one reason, right? So ceramics are heavy, and if you were to try to pull it up out of the goo, it'd be fine for your small parts, your laboratory samples, maybe something as big as a tooth. But when you talk about immense parts like a heat shield or a larger ceramic piece, they get so heavy that they would start to delaminate from the build plate. Also, you would have an immense amount of supports that would be needed to hold it on.
That's a good point.
That's another problem. Cutting supports off a ceramic leaves either a vestige that's very hard to deal with, or you would also potentially chip the ceramic if you cut it off after sintering. And that goes into the processing.
Okay, and you said the laser's up above. So again, gravity is assisting you here.
Exactly.
And it's descending into the liquid goo. And then up above, now this is a 405 nanometer laser, right?
Correct, correct. So it's firing with enough power to get through the technical ceramic and resin to build it on the build plate or on the previous layer, right? So like your mono SLA is also 405 nanometers, but it doesn't fire at enough power through the screen to cure the ceramic.
That's what I was wondering, right?
Yes.
Because I know that, consumer-based 405 nanometer, it's what a lot of the resins are out there that are designed for. And so I was like, well, then why is this way? It's like, it's the power. So that light source isn't enough to cure a technical ceramic. Right. It has to be a laser light that's doing it.
Yes, you can do it with a high-powered DLP as well, but it would have to be a very high light intensity. And the struggle with mono SLA is if you go up to that high light intensity, you start burning the screen. And the screens don't last very long at all.
You don't want to do that.
No, then if you've ever had to change the screen on your mono SLA, it's no fun.
I have, and it sucks.
It stinks.
Now, this has an encoder?
Yes, it's a recoater.
Recoater, I'm sorry, recoater.
So it coats, and then it goes back, and you get a nice even layer of ceramic, and then it goes back and recoats, getting the precise layer thickness that you're looking for.
What is that thickness?
50 microns.
That's not a lot.
That's the half of a human hair.
That's really not a lot. And the recoater, like I have a silicone spatula, and I recoat the pan of eggs as I'm scooping it. But I would imagine at a technical level, how does it maintain that 50 micron height? What is What is in the recoater that's actually doing this?
Right. Attached to this red thing, there'll be a metal blade, and then you'll see this is actually moving on a block of granite.
Like countertop granite.
Right. So this doesn't move. You see the laser is mounted to that same piece of granite.
Oh my gosh, this
So
is
it
granite.
doesn't-
I didn't realize this is granite too.
It doesn't move relative to this, so that laser is incredibly precisely located. So you can print details down to 60 microns in layer thicknesses of 50 microns, making incredibly detailed parts. So when you're building your gyroid, when you're building something like a dental piece or a bone, you can have very fine meshes that the bone could then grow into. When you're building a gyroid, you can make a very fine gyroid structure.
Wow, that's just neat. I love hearing that, and it boggles my mind that this is like granite countertops. When you think of granite,
Yes. So your granite countertop would be about that thick. This is substantial industrial grade piece of equipment. This is not a household piece of equipment. These are expensive,
Obviously.
a little bit more expensive.
You're not
and
serving breakfast on this granite.
the precision that we can achieve with this is unparalleled in the industry. So the other interesting thing with a continuous laser, if you need a really precise line that you're drawing with that laser, as opposed to a DLP, is forming pixels, right?
Oh, right.
So those pixels are little squares. So as you're drawing a line with a screen, you're actually forming a linear stepping of a bunch of little stepped pixels.
I understand. I know where you're going with this.
Right. So as you get bigger, the pixels become more pronounced. So if you were to make a bigger format, you would just have a bunch of very, very visible pixels.
Oh, that's not good because you're not machining
No.
ceramics. What you get is what you get, right?
Right. So the continuous line, the continuous laser, makes a clean, continuously flowing shape that is then, for very, very small parts, it's important because you can get very fine detail. For large parts, you can get very consistent detail without the little notches. Again, ceramics don't like sharp edges. They don't like corners, and any little fine little notching is going to cause a surface issue that can lead to stress and fractures.
So now the print is done and the recoater has swiped all it needs to swipe and the part is in the goo. What are the next steps?
Right, so it will then, once it's completely finished, it's printed all of its layers, it'll emerge from this platform. This platform here is our 100 by 100, appropriate for laboratory use, some small production of small parts. Our medium-sized printer is 330 by 330, and then our large industrial or large part printer is 600 by 600 by 300 deep. So it can make immense parts.
Ceramic piece, 60 centimeters by 60 centimeters by 30 centimeters.
Correct.
Is possible.
It is possible. We have printed them. There's many applications for that, both space and industrial uses. We're talking more and more about the CHIPS Act and making wafers here in the United States. And to do that, we have to highly automate it. To run those parts through a wafer manufacturing process, it's incredibly high temperature. So the wafer will actually ride on what's called a wafer carrier. That wafer carrier is made out of ceramic. It's made out of alumina. And that ceramic will then, could pass heat through it. It can pass cooling through it if we 3D print it.
There we go. And it has to be large enough to carry the boards.
Yeah, a big wafer. A wafer ring is, 500 millimeters in diameter.
3D printing of these ceramics allow for more functionality and more purpose, whereas before it couldn't have done that.
Right. It was just a block or a series of structures that would then hold all of these wafers. Now we can actually heat them and cool them and run them through faster. And we can make automation of that process here in the United States at a much more efficient pace.
And when we talk about that size, that's 600 millimeters by 600 by 300 tall, when we talk about that size, especially in something like heat shields, you want less parts. You want less open parts because that is where heat can get in, right?
Right, yes. When you're talking about a heat shield on a spaceship, we're going to start talking commercial space, right? You're going to be going back and forth frequently.
I hope so.
Yes, so
Lilu Dallas Multipass.
every joint in between each shield causes drag, and that drag is where the heat builds up. That buildup of heat is where it becomes dangerous for little Joel.
Yeah, I mean, you could see he
Yes.
re-entered
Yes.
inappropriately.
Yes, exactly. Mini Joel, as you said, he has burnt up a little bit because he tried re-entry without proper shielding. So why don't we print a heat shield for Mini Joel?
A heat shield for Mini Joel.
Yes.
You want to start the print and we just do this?
Let's go try it.
Yes.
Yes.
David, I hear the print's done.
It is done, Joel. Okay, so as we were talking, we were going to print a gyroid structure.
May I?
Yes.
Wow, look at that. Oh, I love the surface finish.
Yes, it is a smooth ceramic surface finish with a gyroid infill. And like we mentioned, the gyroid will both help to dissipate the heat through that longer travel, and it will also provide some dead air space as an insulator.
I never thought that gyroid, like the thing that I know, is going to help us keep spacecraft safe. It's just a fantastic thing.
We're at the point where we should start testing these 3D printed shapes for improving and making more commercially viable space travel.
That makes sense. Now, this isn't the actual part. This is an example to show the insides, right? Because we've got more parts here.
Yes, so the actual finished part, once printed and cleaned off, would be like this. The smooth outer surface.
Ah, I see. And you want smooth because in heat shielding, it's less friction.
Right, the nice smooth outer surface with as few little gaps as possible. And then the holes on the back, this is actually for draining the uncured resin out. But then we also envision those holes potentially being used as your assembly aid or to bond to the actual fuselage.
That makes a lot of sense.
One or the other. They're going to have to be there to empty the uncured resin. You might as well use them to positively attach.
That's a great idea. Okay, this is cleaned. The print is done and cleaned and washed. Is that right?
Correct.
What's the next step after this when a print is done?
Okay, so after you clean it and wash it, now you have to debind or remove all of that resin from the printed part. So what you're left with is just the ceramic that's inside of that polymer resin.
Okay. Now you've got an example here.
Yes, so you debind it, you put it in this kiln here, it runs under nitrogen, and it's also able to burn off all of that cured resin to the point where you have just a ceramic. So this would be quite fragile.
I will be very careful with it.
But-
Now, under nitrogen, why nitrogen?
So the inert gas makes it so that you're not allowing oxygen in. The oxygen can also cause popping, like it oxygenates, it's sudden pop, and the pop would cause a crack.
That'd be very bad.
So we want to try to keep those popping and cracking to absolute minimum, nothing. And then you'll see, as you go from
smaller.
A to B to C, this is quite a bit smaller. All of the resin is actually gone at this point. If it's white, there's no more resin, there's no more carbon, it's just ceramic.
It removed it, but in that process of heating it to remove it, it shrunk it.
Right, so the little grains of ceramic that are stuck inside of the resin goo start coming closer and closer together until they're touching. Once they're touching, then you've got a pretty nicely fused and fully sintered ceramic. If you start bonding the molecules or the grains together, you start becoming crystalline and then it becomes too brittle. And you don't want that. So you want it just to be grains close together. That's kind of the basics of ceramic. So that's what we're seeing here.
So it's debound. We have all the resin out. This is a ceramic piece.
That is a ceramic piece. And then what we're going to do is we're going to start that process of fusing the ceramic together called sintering. And once we fully sinter, you will end up with a piece that looks like this. And this piece, as you'll see, is quite a bit smaller.
It's even smaller.
Right.
May I?
Yes, and this one, it would be a hard, dense ceramic. This one has been tested and fired. So that one has got some marks on it, some scars from actually being through a thermal test, a torch test.
And now, when we talk about sintering, what temperature does this have to exist at? And like, what's the timetable for that?
Right, so to debind, it's a very slow ramp up to about 600 C to burn off that resin.
That's this one right
Yes.
here, debinding.
Right, and you stay at 600 C, but that ramp has to be very slow because if you heat too fast, again, the ceramic can crack, right? So you want to, yes,
I've done that.
I'm sure if anyone has ever fired a piece of pottery and you fired it too fast, it cracks. And then all your work to make this beautiful shape is gone. So we're shaping it and forming it, we're cleaning it, then we're debinding it.
But how slow? Like an hour?
No, like 4 days.
Oh, really slow.
Really slow.
Really slow.
So you come up to temperature, and you maintain that temperature for hours to maybe a full day, and then you come back down.
But you have to come back down slowly too, right?
Exactly. So your
That's a long time.
Yeah, your total process is 4 to 5 days to do the debinding.
Good to hear. Now this is sintered.
Fully sintered. Yes.
And what's the temperature here?
So to sinter alumina, we're going to go up into the 1600, 1700 degrees C range. So hot like the sun hot. Right, so in this oven here, or these smaller ovens here, the 3D Ceram kiln here, the sintering kiln, is going up to 1800 C is the max temperature that it can hit safely. And we will take it to 1750 and hold it there overnight. And then come back down and come in the morning and we take our heat shield out.
So then this is a longer process because you're having to slowly do it to cook out the material.
Correct.
This one though, because it's pure ceramics, you don't have to take as long?
Right, and you're not worried about that organic, the polymer popping and exploding and burning, and you get carbon and you never know what, you do know what's gonna happen, and you know that if you go too fast, it will pop.
And ceramics, so you're putting this under 1700 C, 1800 C, and it can hold. And that's one of the reasons why I would imagine ceramics are perfect for heat shielding, because they can take the heat and they're able to dissipate the heat, right?
Correct. And they're a great insulator, not only for heat, but for electronics and other applications, but also they're incredibly hard. So that hardness is also good for durability, for wear resistance, scratch resistance. If you land on another planet and you happen to get it all scratched up from the lunar regolith, this surface is hard and durable against wear.
It's neat that we talked about heat shields in that they are durable and tough and hard, because it could be that other world surfaces aren't very forgiving. Right. And then we also talked about them having to dissipate heat, and we just happen to have something cool over here. And there's a space shuttle right here because this part is for that, correct?
Right. Yeah, so this was one of the training parts, and this was a collectible now because it's no longer in service. So this is part of basically these little black pieces.
Let's go up here, look at that. So the windshield.
Right.
This is what part of the black frame of the windshield.
Right. So this would have been on a training piece. So in 1979, as Enterprise was being developed, they had to try putting these heat shields on. And anyone who's ever been to Kennedy and watched the demo, they talk about how the heat shields were a problem. And they were
nearly 45 years ago.
Right. This was the state-of-the-art technology in terms of how to manufacture a heat shield and how you would actually go about putting it on, taking it off, and reusing it. Because as you re-entered Earth's atmosphere in the shuttle program, these would be, they say, ablated. It would burn off.
It would burn off, right? Yeah.
And then you had to replace a large portion of these. Had to be replaced.
Every time.
Every time you re-entered. And they were expensive.
Okay, so this is where it gets crazy. This piece right here is to scale, and hundreds of these would be around the windshield.
Right, and the entire shuttle had 23,000 heat shields.
23,000. This is the original. This is Space Shuttle. This is 70s and 80s technology.
Yes.
Okay, what was the cost for one of these?
Something that size would have been around $10,000. The bigger shields would have been almost $50,000.
And there's thousands of these on the spacecraft. And so obviously having them ablate or burn off is terrible, because you want, the whole point of spacecraft and space travel is reusable. Right. Reusable, okay.
So this was as reusable as we could get in 1979, 1980 technology.
Yeah.
And so now the task is, how do we do commercial space, right? How do we have a vehicle go up to a hotel in space and come back, let's say 5 times? Totally reusable 5 times. There and back 5 times. That means it has to go through the atmosphere going out and coming back 5 times, but it's a very rough re-entry.
Now, when we talk about that though, right, we talk about this, and the reason it's rough is because there are so many, like all of these mating surfaces of a heat shield having to keep a spacecraft safe, and there's hot spots that can develop, and if one fault, it's not optimal. And so this is where additive ceramics really empower the future of space travel, right?
Right. So we look at not only gyroid shaping and forming and be able to create the shape that could potentially have less drag, but because we can also print larger parts we can now make bigger heat shield, therefore less gaps, less fusion of those gaps together, and less drag from having so many little tiny heat shields all over.
So this is not a heat shield here, but this really illustrates the size of a 3D printable technical ceramic that
Correct.
could be used for heat shielding. And it's not just being able to recreate this shape. The whole point of additive is to be able to solve that problem in a better way with less material, less money, or to be able to make more of them easily, right?
And the other thing is, to make it more reusable, you know, we would want to have a hard, durable outer skin, whereas the soft foamed aluminosilica base of a original shield was very fragile, and any little micrometeor or any little piece of debris during exit or launch would hit that, and it would potentially damage the shield, and that can be quite dangerous on reentry.
People don't a lot of times realize that when we talk about the future of space travel, it's not just being able to create reusable vehicles from here on planet Earth. We have to be able to service those vehicles, not just within atmosphere, but potentially on other worlds. And this is how we get there.
Right. So imagine 3D printing your heat shield or your repair out of lunar regolith. You know, take that material, put it in the resin, you know, print, have a little printing farm there. And
Lunar regolith, Martian soil, the possibilities are endless.
right. We could potentially do that in space as a re-entry service plan. You know, you come in and before you re-enter the Earth's atmosphere, you get your spaceship checked out, you know, replace a couple tiles, check the tire pressure, clean the windshield, maybe an oil change, you never know. Yeah, there'll be a little dude there.
Make it safe for your travel, right?
Yeah, there you go.
It's so fun to think about. Now, it's time to explore the real reason why I'm here at 3D Cerem's Sinto, and that's to keep Mini Joel safe in his spacecraft on re-entry to Mother Earth.
Correct.
How did this happen?
This happened.
David, we're set up here.
We are.
Now, this metal is what?
Aluminum.
Oh, okay.
Basic aluminum, standard grade. So a lot of aircraft are aluminum skinned, so that's what we figured we would demonstrate. And then, yeah, we'll try it with just a torch test.
With just a torch. This is bare aluminum spacecraft re-entering the atmosphere with Mini Joel as a pilot.
Right, and absolutely no assistance from any kind of thermal protection system whatsoever.
This is awesome.
Ready?
Let's see. I think so. Just we're entering the atmosphere.
And as you see, without any heat protection, the aluminum starts to fail. And very quickly, it'll fail and burn through. And poor little Joel, suddenly on fire.
Fatality.
So, this is why aluminum spacecraft should not enter an atmosphere without some form of heat shielding.
Exactly, because the amount of drag on the outside of the fuselage would heat up so much that it would just burn off the aluminum and poor little Mini Joel on the inside.
But now, though, with ceramics, we have the ability to protect not just the aluminum spacecraft, but the Mini Joel inside. So why don't we get set up, and why don't we test that?
Absolutely. Next up, heat shields. Keep it on the heat shield. You'll see the heat shield will start to get hot. It'll start to get red hot. But little Joel is still fine.
And we're out of atmosphere. Look at that. I can hold it. I can freaking hold it. Mini Joel it's fine.
Right, exactly. So the heat shield totally protects it, dissipates the heat. The spaceship is fine, Mini Joel is fine, re-entry happened, everyone's safe and back at home.
And this is thanks to not just ceramics, but 3D printed ceramics.
Right, that gyroid shape that we talked about, the air dissipation on the inside, the ability to have a nice, hard, smooth outer surface, all those things only possible with 3D printed ceramic.
Listen, you know what? We've proven that this works, and there's a lot of really cool technical details about the 3D printed ceramics that 3D Serum Sinto does. And so I want you to look to the audience and tell them where they can go to find out more information.
So please go to www.3dceram.com to get more information about the printers, the materials, and what the 3D printing of ceramics can do.
And we'll put a specific link in the description that'll take you to a specific spot to kind of give you some more information and stuff. If you made it this far, you're awesome. Don't forget to hug each other more, fight for a cause you believe in, enter all the atmospheres with 3D printed ceramics. Let's go with it. And as always, high five.
High five.
Yeah.